Dear students, I, Professor Bhuva, Dr. Subhash Technical Campus, Junagadh. Today we will discuss about last module of our design of steel structure, its plastic design. So in that we will discuss today's in this video introduction, plastic hinge and the concept, plastic section modulus, shape factor, collapse mechanism and determination of collapse load. So start with the first introduction. So in the elastic method of design, also termed as working stress method or you can say allowable stress method, and deformation are computed at working load using elastic property of steel that normally we have to design. After that, the working stress design limit the structural usefulness to steel up and allowance stress on permissible stresses which will below the elastic limit is called yield stress and it is taken as design criteria. So in this plastic method of design, ultimate load is taken as a design criteria and hence the structure design using working stress method may be heavier than the design by plastic method. So the working stress method utilizes the strength of steel up to yield stress, while the plastic method is utilize the strength of steel beyond yield stress. You can see in the graph of elastic limit. So the plastic method of the design utilize the reverse strength of steel beyond the yield strength up to the ultimate load point. So the plastic method of design give a economy design as compared to elastic. So that's why in new code after the revision of IS 800 the plastic code has introducing for the material safety and you can see the graph of elastic perfectly plastic. You can see the elastic limit. After that it should be a constant and we when consuming unloading condition will we use the plastic state. Now next slide, assumption. So there are the some assumption to achieve the plastic state or yield stress below the load failure. So first the materials is obeys the Hooke's law till the stress reached by F5. Second one, the yield stress and modulus of elasticity have the same value in the compression and tension. Third one, the material is homogeneous and isotropic in both the case of elastic and plastic states. Fourth one, plane transverse section remain plane even after bending and the effect of shear is negligible. The cross section of beam is symmetric about axis through its centroid parallel to the plane of bending. The influence of normal and CL force on plastic moment is not considered. There is no resultant axial force on beam. The material is assumed to be sufficiently ductile to permit large rotation of the section to take place. And last one, no instability occurs in any member of structure up to collapse. So the cross section of the beam is symmetric about axis through the centroid and parallel of the bending and every layer of material is free to expand and contract longitudinal and laterally under the stresses as it separated from the other layer. So these are the few assumptions that will be satisfied to reach the plastic state. Now process of yielding of section. So let a cross section increase gradually within the elastic limit is M is denoted by M is equal to gamma into Z, while Z is section modulus, Z is generally I by Y. Now elastic limit minus yield stress reach is equal to My. So now including the yield stress, so normal M converted into My. So My is equal to gamma into Y into Z. So when the moment is increased, yield stress into inner when the moment is increased. So the yield stress into inner fibers, remaining portion still elastically. So finally the entire cross section are yield. So we allowed into the inner fiber as a yield stress. Remaining portion are in elastic form. So change in a stress distribution during the yielding you can see in the figure. In first case, M should be less than My. Now we increase the moment. At that time M should be My. You can see that figure sigma y, sigma y. Now we again reach or increase the moment. So My should be greater than M but less than Mp. You can see that figure of distribution. And finally when we reach up to the plastic moment is denoted by Mp. At that time sigma y of tension and sigma y of compression both the shape are same and passes through this plastic hinge. So these are the change in stress distribution during the yielding form when we applying or increasing the bending moment. Now inverted T shape, you can see one example of inverted T shape. You can see that profile of T. Now centroid axis passes through this flange of T. The maximum moment for inner elastic condition you can see that sigma y. It should be reached up to final stage of partially plastic. At that time it should be noted at equal axis. But when we achieve full plastic state, you can see the equal area axis. At that axis, both the shape of tension and compression are equal. So in this process, we can allow the full plastic state. So this is the example of invert T-beam. Now what is plastic hinge concept? So when the section is completely yielded, the section is fully plastic. So when we completely achieve the yield stress, automatically our section is fully plastic. So fully plastic section behave like hinge or plastic hinge. So we all know that plastic hinge is defined as yielding zone due to bending in a structural member and which large rotation can occur at a section at constant plastic moment MP. So that's why we will corresponding bending moment is called fully plastic moment MP and is denoted by Fy into Zp. Now plastic section modulus and shape factor. So what is plastic section modulus and shape factor? So the plastic moment resistance MP you can see in this example of one section. Here the bottom is tension at area is equal to A by 2 into sigma y and due to CG2 central axis is Y1 YT and compression is again A by 2 into sigma y and the centroid is YC. So similar sigma y and Z. Now moment at which the entire section is under yield strain. It means we have to achieve plastic set. At that time both the area of tension and compression are same. So for the same assumption we have to take C is equal to T. So area of compression divided by stress in tension is equal to area of compression divided by stress in compression. So you can see finally the area of concrete is equal to area of tension is A by 2. Total area divided by 2. Now divides the cross section into two equal parts. C is equal to T is equal to A by 2 into sigma by y. So finally coupled due to A by 2 sigma y is equal to A by 2 sigma y yc plus yt. Here the yc and yt is the centroid of compression and tension. So we have to take constant sigma y multiply by Zp. Here Zp is nothing but plastic section modulus. Now how we calculate the shape factor? After calculating the Zp, Zp divided by Zd, it should be greater than or equal to 1. It is nothing but shape factor. So the shape factor is a property of cross sectional of shape. It is independent of the material properties. So generally shape factor is denoted by plastic moment divided by yield moment. Now what is the advantage of plastic design? So it's saving the material over the elastic method resulting in a lighter structure. Design the moment can be calculated rapidly. It gives an idea about the types of collapse and the strength of structure. No effect due to change in temperature, settlement support, imperfection, etc. Design is very popular for the design of beam and especially for portal frame. Now, few are the disadvantages, which are, so there is a little saving in column design. So that's why we not introducing in column. We will introducing only the beam and portal frame. Second one, disadvantage, it is difficult to design for fatigue edge and its the structure is complicated. It is difficult to obtain the collapse load. Next, shape factor of various cross section. Now we take rectangle cross section having d depth is equal to d and width is equal to b. So the section modulus z is equal to I by y. So I for rectangle section bd cube by 12 and y for d by 2. So finally z we will find out bd square by 6. Now introducing the plastic moment zp is equal to a by 2 yc into yt. Now what is yc? D by 2 into 2, it means d by 4. Then area should be b into d divided by 2, d by 4 plus d by 4. So finally we got zp is equal to bd square by square. Now according to our equation of shape factor, plastic moment divided by yield moment. So the ratio or the shape factor of rectangle section is 1.5. Likewise, any circular of section you can find out the shape fraction. Same one, second one will be example of circular section. So Zp is equal to a by 2 yc plus yt. So pi by 4 d square, pi d square divided by 8, 2d upon 3 pi plus 2d into 3 pi. It's nothing but your yc and yt. And finally Zp you have to derive d cube by 6. So our plastic moment should be pi d4 by 64 divided by d by 2. So finally our z is pi d cube upon 32, and when we calculate shape factor zp upon z, so it's because of 1.7 for the circular section. Likewise we calculate triangular section, the shape factor should be 2.346. Next, for the I section, the shape factor should be 1.135 and MP should be 59.6 kilonewton into meter. Now what is collapse mechanism? So the beam mechanism determine the beam of frame of collapse after first plastic hinge should be provided. Now what should be the plastic hinge and when it's occur? So the plastic hinge from in a member when the maximum bending moment location. However, the interaction of two members where the bending moment is the same hinge from in the weaker member. Generally, hinges are located at the distant ends, interaction of members and point of load. At the connection involving change in geometry, at that time we also provide the plastic hinge. And at the point of zero shear in span of loaded by UDL throughout the beam. So these are the plastic hinge it should be occur. So in our first case beam mechanism, so we will provide below the point load plastic hinge should be provided. After providing the hinge you can see the effect in our figure what should be the effect of plastic hinge. Next, intermediate beam and frame more than one plastic hinge to develop the mechanism. Now our beam is intermediate, then we should provide more than two plastic hinge. One at the maximum bending moment, it means below the point load, and two are at the different end. So the plastic hinge develop at the ends first becomes beam becomes a simply beam and plastic hinge develop at the center for beam mechanical or you can say beam collapse. Now intermediate beam more than one plastic hinge to develop the mechanism. At that time we should take the prop cantilever beam. So the plastic hinge develop at the fixed support first beam and a simple beam. Plastic hinge develop at the center from the beam collapse. So now we provide the plastic hinge as a fixed. So our beam converted into the simple beam and then we provide at the center when the maximum bending moment should be occur. Same way parallel mechanism or you can say the sway mechanism. So we can show in previous slide where it's occur of plastic hinge. So at the interaction and when the connection between two members. So we should provide at both the end and provided between beam column junction. So 4 hinge should be provided as a sway mechanism. Same way we provide in a global mechanism for the truss, and we analyze the hinge for plastic. Now method of plastic analysis. So first one is static method or equilibrium method. So the lower bound, a load compute on a basis of assumption of equilibrium bending moment diagram in which moment are not greater than mp is always less than or the worst equal to the true ultimate load R should be satisfied. Now in second case it means kinematic method or mechanism of method, or you can say the virtual work. The work performed by the external loads is equal to the internal work absorbed by the plastic hinge. At that upper bound, a load computed on the basis of assumption mechanism is always greater than or at least equal to the true ultimate load. So these are the two methods when we introducing the plastic analysis. First one is static method and second one is kinematic method in upper bound theorem and static theorem with lower bound theorem. So these are the two types of method that we introducing the plastic hinge. Now plastic hinge occur that will be discussed at the point of maximum moment. At the connection involves the change in geometry, it means I or 2I under the concentrated load at the point of zero shear in a span loaded through uniformly distributed load. Now first determination of collapse load. How we calculate the collapse load? So we will take simple beam and we should provide one hinge below the point load. So our MP, it means plastic moment is WU divide WUL by 4. U means ultimate load and finally WU, you can see that 4 MP by L. So it should be inverse process. We'll be calculating the collapse load. So this one is M loaded to elastic and up to we increase the moment should be converted into the MP due to providing the plastic hinge. By virtual work we will see elastic load divided by ultimate load. So VU is equal to, now you can see provided the theta hinge at the point of concentrated load. So 2 theta should be occur. So at that time what should be the virtual work? 1/2 theta. So WU 1/2 theta is equal to MP into T theta. So finally WU, it means ultimate load, we will take 4 MP by L. So by virtual work we will identify this MP. Same way for the fixed beam with UDL we should provide 3 hinge both at hand and one is occur when the maximum bending moment. So M center should be WL bar L square by 24, M and ends should be WL square by 12. It should be less than M center. So hence plastic hinge will be developed at the end first. You can see in this figure, first we provided both the end and third will be provided at the center. So equilibrium condition 2 MP is equal to WU L square by 8. So finally WU is equal to 16 MP by L square. Now we will same check with the virtual work. So 2 into WE by 1/2. So 0 plus 1/2 theta divided by 2 is equal to MP is equal to theta for left hand, 2 theta at the center and 1 theta for right hand. So it is totally 4 theta. So finally WU is equal to 16 MP by L square. Both the case are same. Either you should use by equilibrium or static force or use by kinematic or virtual work. Both the WU are same for any case of beam. Third one is fixed beam with point load. So at that time same 3 hinge are provided, first at end, second in end and third one is center. So at the both the end when hinge is provided, theta should be located, at the end the center it should be a 2 theta. So same virtual work WU 1/2 theta is equal to MP theta plus 2 theta plus theta. So it's nothing but external work done is equal to internal work done. So external work done is equal to W, then center 1/2 theta and internal work done is equal to theta, 2 theta and theta. So finally W is equal to 8 MP by L, and under equilibrium condition the value should be same. Same way fixed beam with eccentric point load, so WU is equal to 2 MPL divided by AB, where A and B are the projection of larger and smaller is related to end. Same way we will derive in a virtual work, so WU is equal to 2 MPL by AB, the same condition as a equilibrium condition. Now prop cantilever with point load mid span, so it should be a first converted into the simply beam, so that's why one hinge should be provided at the fixed end and second hinge should be provided at the center. So virtual work WE is equal to external work done is equal to internal work done. So WU 1/2 into theta. What should be theta for fixed end and 2 theta for mid. The third one is already hinged, so we not consider theta over the next end. So finally WU is equal to 6 MP by L. So as per my suggestion, virtual work system is very easy and understanding to finding out ultimate low. So we always go for virtual work until and unless it's not compulsory to derive the equilibrium condition. We will also always use virtual work principle to finding out collapse load, or you can say the ultimate load of plastic. Same, sixth one is prop cantilever with UDL. So the maximum positive moment occurs at a nearer to the end, and at the collapse load we can find out at x2. So ME WU L x2 divided by 2 minus WU x2 square by 2. So finally MP we will discuss in equation 1. For the maximum case we will take that summation derivation with the respect of E, ME upon dx2 by 2 is equal to 0. So finally we got x2 is equal to 0.414 L, and for that WU is equal to 11.656 MP by L square. So these are the method to finding out collapse load for the different section, but we go for the virtual work principle. Thank you friends.